Hello guys, in previous video we saw how face recognition works and why we need to reduce dimensions of image before recognizing face. So in this video I am going to tell what is PCA or principal component analysis, or how we can use this for reduced dimensions. So before understand what is PCA, we have to understand what happens when we reduce dimensions. So for that, take a look at this coordinate system example. So you can see in this coordinate system there are 6 points and there are 2 dimensions, x dimension, y dimensions, and each point needs 2 components for tell its position, its x component and its y component. Each point needs its 2 components for tell its position. So for 6 points there are like 12 components, but you can see there are not much variation in y-axis. The points are only varying in x-axis. So we can say that y component of y position component of these points does not carry much information. Only x component is telling in which direction points are going, means in which directions are variation. So we can say we can remove y-axis, we can only keep x-axis, and we can tell that this is at like we can store a location of a direction in which there is maximum variation, and we can store positions of the point respect to that value, means like this is 1 2 3 4 5 6, and now we can need only 6 components for store their position, and we can get original positions of these points on by using its direction of component, principal component of maximum variation, and position of points on this principal component. So let's take a look at another example. You can see there are like 7 points, so we need 14 components for tell their position in this coordinate axis. So but you can see this they are like has maximum variation in this direction. Okay, so we can only write their position respect to only this direction, and we can store equation or information about this principal component one time, and we can store 1,000 points, like lakh points according to this axis. So we are kind of like changing means like shifting to new coordinate axis, and now we need only 7 components for store these points and 2 components for store the information of principal component. So let's say data points are not arranged in like uniformly, they are like this zigzag pattern. So now also we can see in which direction there is maximum variation. Maximum variation is like in this direction. Okay, means like in this direction of x equals to y line. So we have to find positions of point respect to these lines, means we are going to project these points on these lines, because we have to find like a position of this red point on this line when we see in reference of this line, and this point, this point, each point. So for projection we already know we can use formula, means this is a vector b and this is vector a, and we want to projection of a on this line vector b, means a1. So for that we can use like a1 will be a dot b. Here a is a point's position, which was this red point, and let's say point is 3x plus 4y, x and y are unit vectors, and b is new coordinate axis. In our case b is this line. So we can project here b equals to x equals to y, because x and y are increasing in same order, and b should be unit vectors, so we divide it by its magnitude √2, then b will be 0.70x plus 0.70y. So we can now find a1 by multiplying this and this and this, because this is unit vector, so it will be get cancelled. 3 into 0.70 2.1, 4 into 0.70 2.8, so 4.9. so we have found position of this point in reference to this line. This is a1. So we are going to find positions of each points with this in reference of this line, and we are going to store these values. So after arranging those points on this line, we will get something like this. But if we want to create their original positions, means if you want to go back, so then it will be on this line, because we are only storing positions of points with respect to maximum variation line, so we don't know their original positions. So our new coordinates will be these yellow points, but original coordinates points were these red points. So if we see these both graph, we can see that they are not exactly similar, but they are almost similar. So I'm going I'm telling this example because I want to understand that when we apply dimension reduction algorithm, we always lose some information, and how much information we lose, that depends on how much dimensions we want to decrease. So up to now we have understand that for reduced dimensions we have to find out the dimension in which maximum variation exists, means in which dimension there is maximum variation. So this happens in PCA, in which means there are like thousands and lakhs of points, and we have to first find out the maximum variation dimension, and then we have to find out second maximum variation dimension, because there will be not always like two dimension. Image will be of like 50 by 50, so 2500 dimensions. So there will be going to very large dimensions, and we are going to find out very less dimensions. So we are going to find direction of maximum variation, then second maximum variation, like this. So in PCA used for dimension reduction means finding new basis vectors, means we are finding new coordinate systems and shifting old points to new coordinate system. PCA is unsupervised, means it does not care point belongs to which class, means um, like in face recognition, points showing to face of which person, it does not care. It only finds in which direction all faces are going, showing maximum variation. So PCA targets to find direction of maximum variation. So now we have to find direction of maximum variation. So how can we do that? So we are going to take this example for find a direction of maximum variation. Here I am taking example of this image. Image is a matrix to means this every image is like a matrix where their positions are showing their pixel intensity. So this is original image in vector form, sorry, matrix form. So we convert that into a single vector. So here this first pixel will be different for all images. So we can say this is a like x direction, means this is a first dimensions for all images, this is second dimensions for all images. So we can say there are like n square dimensions, because originally this was n by n image. So when we created converted this into a vector, it becomes n square cross 1 vector. So we get n square dimensions. So this is our image, and this is like its pixel intensity at that points. So this was original 3 by 3 image, so it will originally 3 by 3 matrix. So when we arrange those pixels intensities value in array, it becomes n square cross 1 array of dimension n square cross 1, and n square are its original dimensions. So we can say that each image having like very large dimensions. So if we create an we create array from each image and keep adding like this first image, second image, third image, fourth image, and like all images. So it become a matrix of n square cross t, means first we created a single image into an array, and then we added to its matrix, then created second image into array, and then added to its matrix. So this is matrix of all the t images. T is number of total images. So our matrix becomes n square cross t, means n square is dimensions of these images and t are total number of images. So this is first dimension of first image, second image, third image, like this up to t images. So this is our matrix, images matrix. So we need to find direction of maximum variations. So we are first going to like find mean. We can find mean in each dimension easily. Means like if you want to find dimension mean in this direction, we are going to sum values of these all points and divide by t, and after that sum of these points and divided by t. So this will be our mu1 mu2. So easily we can find mean. And step 1 for find our means for achieve our target, first this is first step, we have to subtract mean phase. So our original image matrix is R, and after subtracting mu vector it becomes M, and this is our mean. Means we are going to get vector and vector of mean, this is n square cross 1, and we can convert back into this like n by n by arranging back into matrix form, and we can display it like an image. So this is our mean phase, and we subtract it from original image. So now our matrix becomes M. So for achieve our target, our second step is find new bases, and new bases can be found by finding eigenvectors of the covariance matrix of images. Means we are going to find a direction of maximum variation. So for find direction of maximum variation, we are first going to find covariance matrix, and then we are going to find its eigenvectors, and those eigenvectors will be its principal components. Means they are going to be direction of maximum variation. So we have to find eigenvectors of covariance matrix, and our covariance matrix will be this C11, C12, C11, C1n square, and it will be n square cross n square covariance matrix. And it is very little hard to calculate direct this covariance matrix, so we are going to use SVD. But before that, I'm going to tell why this is hard. If you want to skip, you can skip direct to SVD, but first I'm going to tell why this is hard. Means if you want to find diagonal entries like C11, C22, we have to, then it will be variation between same direction. So we have to understand what C11 tells. C11 tells variation of dimension 1 with dimension 1. Means it is just a variance, not covariance. But what C12 tells, it tells variation of dimension 1 with respect to dimension 2. This is covariance. So all the diagonal entries are just variance, and all the non-diagonal entries are covariance between those dimensions. So we see that originally these are dimensions, dimension 1, dimension 2, dimension 3, dimension 4, and this is n square cross t matrix. So when we find a covariance matrix, then all the diagonal entries are only variance of these dimensions, and covariance non-diagonal entries are covariance between those dimensions like 1 and 2. So here for diagonal entries we are finding you already know maybe formula for variance. It is x minus x bar ka square and summation on all points. So what we are doing for like we want to find C11. So this is first dimension, and we want to find variation of this dimension with respect to itself. So for this is a point minus its mean, like means first value, and this point minus first value. Means for first dimension we are going to find pixel minus mean ka square plus pixel minus mean ka square, intensity of this pixel minus mean ka square, and we are going to do this on this all images, means t images. So like this we can easily find value of C11, and like this C22, C33. But if we want to find C12, means variation of dimension 1 with respect to dimension of 2, then we are going to do like this: pixel intensity of this image minus mean into pixel intensity of this image minus its mean, and plus some pixel intensity of this image minus this mean into pixel intensity of this image minus this. So means we are subtracting mean and multiplying these like both dimensions, because we are finding C12, means variation of dimension 1 with respect to dimension 2. So we can do this summation on all images and can find easily. Means for like diagonal entries we are just subtracting mean and taking square in same direction, and for non-diagonal entries like C12 या C21 both will be equal. So for C12 like this is first pixel intensity minus mean for first image, because k is from first image to last image, and it's subtracting mean from second image pixel intensity and just taking sum. So you can see we are subtracting mean, but we already have a matrix in which we subtracted mean. So instead of rik minus mu I, we can just replace with m, because mean of m will be 0, because we already subtracted mean. And we can also use this formula, but we are not going this formula use because there are n square dimensions, so it will be very calculative to find covariance matrix, because there will be very many combinations for like C12, C21, C32, there are like many combinations, so it will be very calculative. So instead of that, we are going to use SVD for direct find eigenvectors of covariance matrix. Means if we apply SVD on our image matrix, then we will get directly eigenvectors of covariance matrix, and this was our original target. Means we want to find the eigenvectors of covariance matrix, because those eigenvectors will be new principal components, new axes, new bases. So we are going to use SVD, and if you don't know much about SVD, I also created another video and posted a link in description, you can watch that. So what does SVD does? It is a method of decomposing a matrix into other matrices. Means if you apply SVD on our original image matrix M, it will divide into three matrices: mu, sigma and V. So our original image matrix was M of dimension n square cross T. Then we will get three matrices: U of dimension n square cross n square, sigma of n square cross T, and V transpose of T cross T. And here U is a matrix of eigenvectors of covariance matrix of M, and we want to find eigenvectors of covariance matrix because there are new principal components. And sigma is diagonal matrix and eigenvalues of covariance matrix of M, and they are very useful. Means when we find eigenvectors, then it will tell let's see go back just for a moment. So eigenvectors tells in which direction is there is maximum variation. And what does eigenvalue tell? It tells how much variation is in that direction. Means if you want to find eigenvalue of this vector, it will be large than eigenvalue of this value vector. Means because there is more variation in this direction respect to variation in this direction. So with the help of SVD, we have found eigenvectors or direction of principal components, and eigenvalues or quantity of means variation, means how much variation that vector having. So you can see that we have found n square cross n square vectors. Means this is a first principal component, and it is shown in it is represented with the help of new original coordinate systems. Like if we go back and see this image, means this was our new principal component, but we are representing this component with the help of old coordinate systems, x component and y components. So we have to use old coordinates for show direction of new component. So we are means like this is our first principal component, this is our second principal component, this is our third principal component, and this is n squared principal component. So these are new coordinate system or new axes in which we are going to represent our old points. So you can see they are like n square dimensions because they are like n square eigenvectors. So originally dimension of our images were n square, and now also n square. So where is dimensional reduction happens? So we can see that if we draw graph of eigenvalues, So eigenvalues are decreasing rapidly, means eigenvalue respect to first vector is very high, and then second vector low, third vector odd low, fourth vector low. So we can see that after some points there is not much variation in direction of that eigenvector, means only starting few eigenvector has maximum variation, then it has only less variation. So we can say that if we choose only first few like p, if we choose only first few p eigenvectors, we can represent whole data by only losing just some less, very less information. So we dimension reduce from n square to p, where p is less than n square. So we choose a value p which will be very less than n square, and that will cover whole information with dimension reduced. So how can we find value of p? So we are going to take sum of eigenvalues, let that will be s, and we want to at least 90% of information conserved. So we make a new variable sum required s of 90%, means s into 0.9, and we keep adding eigenvectors from first eigenvalues. This is misspelled. We keep adding eigenvalues until sum reach s cross 0.9, means we find a number of eigenvalues which can be represent 90% of whole sum, and by this we can easily find value of p. So after finding value of p, we can only choose starting few vectors, and dimension will reduce to n square cross p. Originally there was n square vectors, now only has p vectors, and these vectors, eigenvectors, will be our principal components. And each eigenvector is like eigenface, also called eigenface, means we can represent any image, means we can represent any of our image with the help of these few eigenvectors. And mean means like multiply this eigenvector with 2, multiply this eigenvector with 3, and add them and add mean, we can get any image. We just need to see what are components of multiplication. So initially to 500 dimensions, because I am using a 50 by 50 image, so originally 2500 dimensions, now only have 15, and information lost less than 15%, means I represented all images only just in help of these 15 images. So step 3, new coordinates. So how can we find new coordinates? Because our old coordinates are of dimension n square, and there are all total t images. So and our new basis, new axis are means u vector of n square cross p. So there are like p vectors. So we can find new coordinates by taking transpose of mu metric vector and multiplying with p. So after taking transpose of u vector, it will be of p cross n square, and p cross n square into n square got cancelled, so it will be p cross t. So now we can see our new image matrix M is of p cross t, means total image is t, but all images have only p dimensions. So we can see our dimensions of image decreased very much from n square to p. So now we have our new coordinates, and if we want to go back to our original coordinates, we can go easily. So if we want to get our image back, image will be mean, because we have stored our mean, plus new bases. New bases are of n square cross p, means u vector n square cross p, and new coordinates of that image, means we want to find a coordinate, old coordinate of a single image, then it will be of like p cross 1, its dimension p and single image so 1. So if you multiply n square cross p into p cross 1, it will be n square 1. So that will be original image, or we can say image equals to mu plus u vector, and this is our new coordinates, and whole column of 0th first image. So image dimension will be n square cross 1. So we get our image back, and we reduce dimensions very less from original dimensions. So that's all for this video. In next video I am going to tell what steps or procedure we are going to take for recognize face using PCA. So thank you for watching this video. Please like my video and subscribe my channel.